Hello, so today we're going to try and draw a resting neuron. And by drawing the neuron, hopefully we can understand the way that the resting neuron maintains what we call a resting potential. So I'm going to draw first of all across the page two lines that represent the neuron cell membrane. Draw it with me, but as we draw it we're going to leave three gaps because we're going to put in some proteins that are effectively pumps or channels. So if we start here and draw across, okay, leave a gap, leave a second gap, leave a third gap, and then repeat along the bottom here. So this is effectively the membrane of a neuron. Okay, what I'm going to draw, well, let's decide what's outside and what's inside. So let's make this outside the cell. Okay, outside the neuron. This is inside the neuron. Alright, and what we're going to draw now is some, as I say, some proteins that represent pumps or channels in the membrane. Now, before I do that, just mention some people sometimes can draw some diagrams. You see, we'll have the actual lipids drawn in here, because after all, this is a lipid membrane. We're not going to do that, but you will see it in some diagrams. What I'm going to draw, though, in this bit here is a big circle. And this circle is going to represent a pump. Okay, so I'm going to just change pens over, and this pump is going to be pumping from the inside to the outside some ions, and those are going to be sodium ions, Na+, and it's also going to be pumping from the outside to the inside some potassium ions, okay, K+. But, and this is really, really important, this pump does not pump in an equal way. What it does is this: for every 3 sodiums pumped out, it's going to pump in 2 potassiums. So it's pumping in a ratio of 3 to 2, and that's very important. Now, here I'm going to draw 2 L shapes, upside down L shapes like this. And the top of the L shape is touching. That's because this represents what we call a sodium ion channel. Okay, this is a sodium ion channel. And because this membrane, this neuron rather, is at rest, then these will all be closed. There'll be lots of these studied along this membrane, but they'll all be closed at this point. So nothing's going through that channel right now. Now over here I'm going to draw another 2 L shapes upside down, but this time I'm going to draw them at a slight angle like this. That's to show that this particular channel is open, and this channel is going to be a potassium ion channel. Again, there are lots of these studied along the membrane, and when the neuron is at rest, some of these are open. So I'm going to write some open. Okay, and as a result of that, because we're pumping potassiums into the membrane, some of them will travel back, all right, out of the membrane. So the membrane's a little bit leaky to potassium ions. Now, what's the overall effect of this? Well, inside this neuron, there will also be some big proteins that will be negatively charged. Now, if you imagine the positives and the negatively charged proteins were equal in the numbers, then the inside of this membrane would be effectively neutral. But we're pumping sodium out at the rate of 3 to 2. And although we're losing some potassium this way, okay, we're losing more sodium this way than potassium coming in, and therefore what's happening is inside this neuron we're getting less and less positive ions, and because there are negative anions in here, the overall effect of that is to make the inside of the neuron negative with respect to the outside. Okay, and I'm going to write here minus 60 millivolts. Yep, a minus 60 millivolts, that's what we call the resting potential. All right, that's what we call a resting potential. So this is the inside, this is the outside, and as you can see, because the pump, the sodium potassium pump, we haven't labelled that. Why don't we do that? Okay, this is a sodium potassium pump. All right, and because it's pumping 3 sodiums to 2 potassiums, it means that the inside is becoming less positive, therefore more negative, and compared to the inside to the outside, we have a resting potential of minus 60 millivolts. Now, if you can draw that diagram yourself, and you can understand the way the diagram works, that's great, because that gives you a really good chance of understanding a resting potential, and that means that when we move on to look at an action potential, this diagram is going to be very, very helpful.